Now, what we're going to do in this session, and again, welcome to our ongoing series of training seminars for gibbscam. We are going to do a tutorial mill part. You've all have probably seen this part in the catalogs, and I'm quite sure that you've even attempted to build this part. So what we're going to do is walk through the process of creating tools and applying them to this existing geometry. We've previously held a webinar on geometry creation, so I'm not going to dwell too much on the geometry creation aspect. We simply brought in a part that has already been drawn, and we're going to apply the toolpath to it. What I'd like for you to do is just observe as I walk through the dialogues and tiles and apply the toolpath to the geometry. First of all, I activate the tool list and the cam list. As you all know, the tool list brings up a list of tiles on the left margin of the screen, and this list is fixed. You can't move it anywhere. The scrollable tiles go up to the number 999. Conceivably, you could have 999 tools, although I haven't seen any programs that will work with or that have been created with 999 tools. The second tile is the cam list. This cam tile activates three different features: the machining palette, the process list, and the completed operations list on the right side. On the right side is where the completed operations are generated after we combine a tool with a process. Now, my machining palette is probably more extensive than what you have in your installation. The reason being is that I have more software installed. I have the Pro-Axis suite of 5-axis functionality and jewelry. I also have the volume mill plugin. This volume mill plugin is accessible to all customers on a trial basis simply by contacting the creator and getting a trial version. As I mentioned, we're going to start by creating a series of tools. Double-clicking any one of these tiles will open a dialog window that allows you to define a tool. I'm going to double-click tool tile number 1. The dialog window appears. In the heading, it says milling tool number 1. We see a matrix of tool tiles that are segregated pretty much by category. We have an options checkbox. This options checkbox is used when you need to define a tool outside of these parameters. In other words, if I want a rough end mill with a taper and an upper and lower radius, I can click on options, and it gives me a new picture where I can define the shank diameter, upper diameter, upper radius, a angle on the side, a lower radius, and if it's got a flat at the bottom, I can define that also. So using the options lets us do the same for rough, finish, and ball end mills. In face milling, shell milling, and fly cutting, the options really doesn't serve the purpose that it's intended for. You have better results using these types of cutters. The definition parameters of a tool are based on overall length, diameter, corner radius. If the tool is a sharp cornered, we will use a 0 value here. Number of flutes. Flutes are cutting edges, and you can specify 2, 3, 4, 5 flutes, however many flutes your cutter has. The next dialog is for the length of engagement. This is the actual flute length of the tool being used. You have the option of using a tool holder, custom tool holder, or no tool holder at all. When using a tool holder, we can specify the length of the tool out of the holder, And this is handy when doing collision checking. Tool length offset, cutter comp offset, spindle direction, forward or reverse, and tool ID number. Tool ID number, when active, will override the position number in the tool list. For example, if the first tool that I was going to use in my program was a 1/2" end mill, as you see here, but on my machine, it resides in station number 10. I can call this out as tool ID number 10. The tool length offset, the cutter comp offset will update automatically, and it will override any position that this tool may be in. If I uncheck tool ID number, then the tile number will be used to call the tool. Change this back to 1, and you see that automatically the offsets update in order to keep consistency with the tool ID number. I'm going to leave it unchecked. In this case, I'm going to use the tools in the order of creation. In the viewport here, we see the tool, the holder. Holder selection is done from here. And using the scroll bar, we can select different styles of holders to hold that defined tool. The holder classification or information nomenclature is listed to the right of the viewport. We can show the tool and the holder, or we could just zoom up to the tool showing the nose of the holder. Tool material, selection of the tool material is done here. We got high-speed steel, titanium nitride coated high-speed steel, carbide insert, coated carbide insert, solid carbide, diamond, or other. Other could be something that you specify in your material database, maybe a cobalt cutter, or in the case of lathe work, maybe a cermet or a ceramic insert. Comments. Any comment typed here, for example, let me type in 0.5 end mill. And if I hover my cursor over the tool tile, my comment will appear as the dialog below the cursor. So for quick, easy tool identification, type in a comment. And in the course of your programming, you can always hover your cursor over a tool and determine which tool or comment is associated with that tool. All right, back to the tool matrix. As I mentioned, these are pretty much segregated by category. Rough end mill and finish end mill use the same definition parameters. Ball end mill, slightly different. You got overall length, diameter. We lose the dialog for the corner radius because a ball end mill is assumed to be a full radius cutter. Number of flutes, and once again, length of engagement. Shell mill, face mill, and fly cutter are all defined in a similar manner. You've got overall length, shank diameter, full diameter of the cutter, and you can specify a corner radius, number of flutes or inserts in the case of an insertable face mill, and the length of the body or the cut. Typically, this would be the length of the insert if you're using an insert cutter. If it was a high-speed steel cutter, then you'd want to define the entire length of the flutes. This may be a 6 insert shell mill with the height maybe here 0.625. This would ensure that when you rendered the part, you would see when you've surpassed the depth of cut, and it would show up in red in the rendering. Face mill, defined the same way. And so is a fly cutter. Fly cutter may be a single flute fly cutter. For keyways, Woodruff keys, keyway cutters for undercutting, you can define a keyway cutter as the overall length, shank diameter, cutter diameter, and in this case, we have a provision for an upper radius and a lower radius. If we were using a round cutter, say for example, to generate O-ring grooves, make the upper and equal radius the same, and then we'd add the two radii together to get the thickness of the cut. That would give us an O-ring cutter or a keyway cutter with a radius. Number of flutes, and again, length of cut or thickness of the cutter. As you notice, all these values don't change at all when we change the tool tile. We can always come back and change any of these values as we see fit. A thread mill. Thread mill is very similar to a keyway cutter. Same style of cutter, overall length, shank diameter, cutter diameter, and in this case, we've got the included angle of the thread. In the case of an Acme thread, we type in a 29-degree angle. Number of flutes, and cutter thickness. Cutter thickness requires a little bit of a calculation to get it to render correctly. For example, if I was cutting a 1" 8 thread in a thread mill operation, I would define the cutter thickness as the pitch of the thread. This way, when I rendered it, I would get a correct representation of the machining. To calculate this, you simply divide 1" by the number of threads. In this case, 8. Hit the equal sign, and we get 125 thousandths thickness. If I was cutting a 1/4 20 thread, same approach. 1 divided by 20 equals 50 thousandths. Doing it in this manner ensures that we get a good representation when we render the thread. This is defining a single point thread cutter. When thread milling in gibbscam, we are defining the lowest tooth or cutting surface on the cutter. In the case of a thread hob or an insertable thread hob, sometimes you can generate the entire thread with just one revolution. So what you do is you base the bottom thread of your thread hob at the start of your thread, typically the bottom, and you come up 1, maybe 2 revolutions, and the insert or the hob will form the rest of the thread. In a single point tool, you start at the bottom of the thread and feed all the way up out of the hole. Drilling, pretty straightforward. Overall length of the drill, diameter, included angle. 118 degrees is the default angle of a off-the-shelf drill. If you are using a different angle on your drills, change it here. For example, insertable drills are flat bottom, and I type in an angle of 180, representing a flat bottom drill, and this would render correctly. Number of flutes, and again, all these dialogues here are consistent throughout the tool definition. Center drills. Center drills are a snap to define. We define center drills based on their size. A double-aught center drill, select it, fills in all the dialogues for you automatically. The reason we can do this is because they conform to a standard criteria. Anytime you pick a number 4 center drill, 5/16, you're going to get the same criteria from any manufacturer. Spot drills, overall length, diameter, and the default angle is 90 degrees or 45 degrees on the side. I like to use spot drills for chamfering or breaking edges. And in fact, we'll do that on this part, show you how to do an edge break on the top of a part. Boring bars, overall length, cut diameter. So you want the diameter as if the tool was spinning. Number of flutes. And in this boring bar definition, you have a distance here from touch off to the cutting edge of the boring bar. If your boring bar has the cutting tip right at the bottom, this value would be 0. If you use the old style boring bars with the carbide inserts or blanks, then you would type the distance from touch off the bottom of the bar to the cutting edge. A back boring bar, overall length, shank diameter, cut diameter, number of flutes, and in this case, we have the touch off distance from the bottom of the bar to the top of the cut, which is typically used when doing back counter boring. You want to be accurate in the depth of your counter bore, so we need to specify where the cut is being taken. In the back counter bore, it would be the top of the back boring bar. And as I mentioned, number of flutes, and the same as the regular boring bar, touch off to the cutting edge. That value would go in this dialog here. A tap and a rigid tap use the same definition parameters. The difference is that when you select a tap, you are assuming that you're using a compression style holder, and it would set up a G84 cycle. In rigid tapping, you're doing rigid tapping and it requires a different set of cycle, maybe a G84.1. And this does not use a compression type holder. You'll either use a collet or a end mill holder. Sometimes even a drill chuck, if you can get away with that. Now, tap definition, pretty much the same overall length, diameter, the pitch, or the threads per inch. When you type in your threads per inch, the pitch in millimeters updates. This is a handy addition to the V9 software that allows you to define a metric tap readily when machining metric holes. A lot of times you get a blueprint that has all inch values for the part, but they have callouts for metric holes. We've simplified it a bit by giving you the ability to type in the pitch and directly describe a metric tap. The default angle at the bottom of the tap is 180, assuming a plug style flat bottom tap. Mentioned threads per inch, and this is the length of the lead of on the tap. Spot face, overall length, diameter, corner radius if any, number of flutes. Pretty self-explanatory. A reamer is even easier. It's the same definition: overall length, diameter, number of flutes, and the length of the lead or the non-cutting portion of the reamer. A countersink is defined by the overall length, diameter, included angle at the tip, and in the case of using a countersink with a pilot, you can define the pilot diameter and properly define the angles here. The length of the angle will update automatically based on the diameter, pilot size, and angle. A roundover tool is a corner rounding tool. Corner rounding tools are defined the overall length, shank diameter, body diameter, radius, pilot diameter, distance from touch off to the top of the radius, number of flutes, and the length of the entire tool body. Form tools are user-defined form tools. I will show you how to do one in a second. And lollipop tools are a new addition to the V9. You can define a lollipop cutter for porting work, undercuts, or surfacing work. Let me go back to the form cutter for just a moment and draw a form cutter for you and apply it to the cut. To define a form cutter, you draw the profile of the cutter around the origin of the part. In this case, right here. I'm going to keep it simple and draw it using the mouse line tool. Set my grid to 0.03, my Z value to 0, and I'm going to draw a profile. The profile must be drawn on either side of center line. You can't cross center line on the tool or it won't revolve around itself. I'm going to draw a shank and then come out here and draw a thread hob looking thing. Double click the last point and it will terminate the geometry. The rule for the geometry is that it must be terminated geometry, profile geometry. I then double click on it, open my tool tile, and come over to the apply tile, and there's my tool. Notice that the red plus sign determines where 0 was when I drew the part. Now this would technically be the touch off on my part. I'm going to go ahead and do a quick machining operation with this so you can see what it does. Let's go back to this and simply bring the tool down and put a quick and dirty roughing pass on here. We're going to, that'll work. It's gonna chop into the material, but what I want to do is show you. Actually, it's in this part. We're going to go to Preferences and Auto Tool Size. I guess it helps if I say do it first. Nobody was watching when I did that, right? There it is. Okay, so now you see the form tool cutting. It's very important that you hit the do it command. I apologize for missing that. I'm trying to get a little bit ahead of myself. But anyway, that's how a form tool is applied. Go back to the tool list. And we'll dump that. Make a new tool, and pretty much explains what's going on with the tool definition dialogues. We're going to build some tools and we're going to machine this part. We're going to pocket it out, we're going to drill and tap it, we're going to contour it, and then we're going to remove some material using a free form style of machining. All right, I bring up my view control palette, go to top view. And what I'm going to do is build a series of tools. I'm going to build a drill. This drill is going to be used to drill an entry hole for my pocketing. I'm going to make this drill 1.5 inches long, 3/4 inch diameter, 120 degrees on the angle, 2 flutes, and I'm going to take it out of the holder 1 inch, tool length offset number 1, cutter comp offset number 1, forward spindle direction, and my tool material will be a tin-coated high-speed steel drill. Okay, I'm going to make a comment, call it drill, just for the sake of having a comment. We'll close the dialog, hover the cursor over the tile, and see that it says drill. Tool number 2, I'm going to make that an end mill so that I go in and pocket out the inside of the part. This is going to be a rough end mill. Once again, 1.5 inches long. I'm going to change the diameter to 5/8. You notice that I didn't type in 0.625. I used the 5/8. And when I hit the tab key, it calculates the decimal equivalent for me. I'm going to use a 50 thousandths corner radius, 2 flutes, and I'm going to make my length of cut 0.75, and the length out of the holder will remain at 1 inch. Notice that the tool length offset and the cutter comp offset have updated correctly, 2 and 2. Okay, close this, activate tile for number 3. Tool number 3 is going to be a finish end mill. This finish end mill will be 1.5 inches long. The diameter will be 0.5, same radius, same length of cut, same length out of the holder. So pretty straightforward. The system remembered the previous settings, so all I had to do was change the diameter of the tool. Also, tin-coated high-speed steel. All right, those are the tools that I'm going to use for machining the pocket and the contour. I'm going to build a set of tools to spot drill, drill, and tap 4/4 20 holes. So tool number 4 is going to be a spot drill, 1/4 inch diameter, and 90 degrees, 2 flutes, length out of the holder remains the same, and so the offsets have updated correctly. We'll close this dialog. Tool number 5 is going to be a drill, and a 1/4 20 hole. The tap drill size is a number 7, which equates to be a 0.201 diameter drill. That's the only change necessary. Select the drill, type in the diameter, the overall length, everything else is consistent with the previous input. Now, tool number 6 is going to be our tap. This tap is going to be a rigid tap, 1.5 inches long, 0.25 diameter, and the threads per inch, as I mentioned, will be 20. I'm going to give myself a 40 thousandths lead, and again, using high-speed steel, tin-coated. All right, 6 tools. We're going to apply these 6 tools to the geometry. I'm going to draw an entry hole for my end mill to begin the machining. In order to do this, I'm going to do a multi-tool process. I'm going to use a drill to do an entry hole. I'm going to use a rough end mill and a finish end mill, all grouped together as a process. Select the geometry and do it. So the first thing I do is I bring down tool number 1, the 3/4 inch drill. And this is done with the holes process. I'm going to drill on, I'm sorry, I'm going to pocket this part out to a minus ½ inch, minus 0.5. So I'm going to drill down to 450 thousandths. I'm going to feed in, wrap it out. I'm going to take my dimensions from the tool. My rapid approach plane is 0.1. Top of my cut is 0. At up end, I'm going to go to 0.1. And my depth of cut to the tip is going to be minus 0.45. And I'm going to retract to Z.1. You've got three options for the retract. You can retract to Z.1, which is based on this R value here. I can retract to Z1 inch, which is based on my clearance plane right here. Or I can retract to a user-defined value that I can type in. I'm going to go with the retract to R value. Feeds and speeds. Feeds and speeds, if you have the cut data database, can be selected from the material tile. In this case, I'm machining stainless steel. The suggested surface feet per minute are 45, and the metal removal rate or chip load is 4 thousandths. I'm going to bump this up just to show what we can do with it. Instead of 45 surface feet per minute, I'm going to bump this up to 100. And I want to give myself a chip load of 0.0045, a little bit heavier chip load. Once I've input the values, I can calculate the RPM, calculate the feed, and you notice how these two fields updated. If I was to click RPM and feed, they revert back to the suggested values. Change this again. Surface feet per minute, 500. Calculate RPMs. Calculate feed. Now, this is all based on stainless steel. If I come back over here, change my material to aluminum alloys, in the rot condition, I'm going for 60, 61, change the hardness from 75 to 150, and in my alloy window, I should see 60, 61 as part of my selection set, and I do. So I've chosen correctly, close the dialog, double click the process again. Notice that right off the bat, the RPMs have increased as well as the feed. If I go back to my material dialog, this is the recommended values. I'm going to change them again. Recommend 700 with a chip load of 0.005. Calculate RPMs, calculate feed. That's not too bad. I think I can get away with that with no problem. But you notice how we can change the values using the little feed and speed calculator or using the RPM feed buttons here. Or if I didn't care to use those utilities, I could type in 3,500 and 15 inches per minute. If I introduce a dwell, 0.25, this will generate a G82 can cycle. G81 cycle is generated with the feed in, wrap it out. A G82 is generated when you have a dwell. In this case, I'm going to dwell for a quarter second at the bottom of the drilled hole to make sure I get some good cleanup. All right, so we've got that tool properly defined in the drill page or tab. Next, we go to the pre-mill tab. In the pre-mill tab, I have entry hole with auto Z selected. This means that it's going to drill an entry hole and base the Z value here and give me the option of using a clearance. I can stay away from that value if I wanted to with a clearance. If I wanted to drill out the corners, I could select the corner and give myself drilled holes in all the corners. We might come back and do this. Okay, so the first tool is properly defined. Tool number 2 is going to be the rough cutter. Stage that below process tile number 1 in process tile number 2. This is my rough end mill. And this is going to be done with a pocketing routine, rough tile. We're going to use an offset pocket. The feeds and speeds, I'm going to go ahead and take the speeds down a little bit to 2139. My entry feed looks good at 10, contra feed at 20, not bad. The cut width, 0.2625. You wonder where that value comes from? That is the length or the width of the flat at the bottom of the cutter that is available after the radius. So we have a 5/8 end mill with a 50 thousandths radius. So if you divide 5/8 by 2, subtract 50, you end up with 0.2625. This ensures that we get a proper cleanup as we step over in the pockets. Entry exit moves. In order to use cutter radius compensation, you must have an entry line. Now, an arc is not essential, but you must have an entry line to instate the G41 or G42 command. An entry radius is the ability to arc onto the cut and keep the pressure off the cutter on the initial entry move. Pocket stock, and these values are applied on entry and exit. 90-degree line enters the work perpendicular to the selected feature, and advanced activates the advanced entry exit tab, where you can conceivably get really creative with CRC lines, off part lines, Z ramps, include radius. So you can get pretty creative on your entries and exits. If exit is not checked, all the entry moves will be applied on the exit. Go back to a line with a radius. Pocket stock. How much material do I want to leave on the inside of the pocket for finish? 30 thousandths. Island stock, once again, 30 thousandths. If I wanted to leave material on the floor, I would use a value in the Z stock. In this case, I'm taking it right to finish, so we'll make this value 0. And overlap. Overlap is a feature that allows the finish cut to bypass the entry point by a specified distance, thus eliminating any witness lines on the entry and exit. Spring passes is a deflection pass at the last readings. And use stock and material only are used in conjunction. At a later time, we will use material only. Rapid approach, 100 thousandths above the part. Top of my part is 0, or the top of the cut is 0. Retract 0.1, depth of cut minus 0.5. I'm going to take this one right down to finish. Now, desired Z step. When I type in minus 0.5, the desired value comes up as a 1/2 inch. I'd like to take multiple passes with this cutter, so I'm going to divide 0.5 by 2. The actual and the number of passes appear dynamically, and there's really no provision to change these. Retracts. Retracts, when checked, will force the cutter to wrap it up in Z after each level. If retracts is unchecked, the cutter will stay at depth and reposition at that depth and then feed down to the second or subsequent depth. Now, this could be a problem if there are features or islands in the way, it'll cut right through them. So to be safe, turn on retracts, view your toolpath, and then decide if you want to turn it off. Depth first is used when doing multiple features. For example, I'm doing 2, 3, or 4 pockets, and I've got them all selected as a unit, and I'm going to do all pockets at the same time. I can choose to do the first pocket to depth before moving on to the next pocket. If I uncheck depth first, I'll take the first level pass on each pocket before returning to the first pocket and taking the second level pass or subsequent level passes. Prefer subs is the option for forcing a subroutine for this operation only. And hit flats is a function of solids. Plays no role when machining geometry. In solids, it'll force a cut at each flat on the selected solid. The entry method: auto plunge, plunge, ramp, or helix. Auto plunge, the system will find the optimum entry point and enter the work at that location. When pre-drilling a hole in a pocket, you must use auto plunge. This determines where the end mill will enter based on where the hole was drilled. Plunge is a user-defined location. I can give it a start point inside the pocket, and then it'll feed to the center of the pocket and pocket as an offset shape from there. Ramp is a Z-ramp entry. Z start point, maximum cut defaults to the radius of the cutter. The slope determines the entry angle. Slope and angle are tied together. 0.5, increase the angle. 0.1, decrease the angle. The XY ramp angle, we can enter the work along the X-axis, the Y-axis, a user-defined angle, or the default auto, where the system will determine the optimum entry point and get into the work. Wall clearance is used to keep the cutter away from the walls on entry. If you're doing slot milling, you may want to use a wall clearance to make sure that the cutter enters off the finished wall. Helix, helical entry. Z start point, max cut, a slope, and 5 different helical options. Auto helix end at start point. The helix will end where it began. Auto helix center at start point. Center of the tool at start point. Center at XY position. Helix end at start point. Each one brings up a different set of options. I would suggest doing a helical entry on a part. And once you've got a good tool path, go in there and change it to see the results of the different options. You may end up using a different one than the one you selected initially. In this part, we're doing an auto plunge. Round corners should always be on. This ensures that the tool path will roll around the corners instead of bypassing it to the tangency and then changing direction. If you want sharp corners, give it a 0 corner break. If you want to break the corners, you can type in the amount right here. But as a matter of course, always leave round corners on. You're going to get better results. CRC is on. CRC is cutter radius compensation. We're going to turn that on. And we prefer to climb mill the pocket. Flood coolant is in effect. Patterns is unchecked. Patterns gives us the ability to define machining in multiple locations based on one piece of geometry. All right, so we'll go ahead and we'll close out the roughing process. And we're going to stack one more tool on this process, and this is going to be the finish tool. This is tool number 3. Tool number 3 is going to be a contour cut. We're going to finish the ID of the pocket and the OD of that island with this particular cutter. Change my RPMs to 2500, 10 and 20 for my feeds. Entry feed, contour feed. Entry exit moves are valid from the previous command. And in my stock, I'm going to make this value 0 because I'm taking it right to finish. Overlap, 30 thousandths. I want my last cut to bypass my entry point by 30 thousandths. Rapid approach, 0.1, top of the cut 0. Rapid retract, 0.1, and depth of cut, 0.5. Desired Z-step, 1 step at a ½ inch. Auto plunge, round corners, 0 corner break. Cutter radius comp is on, and flood coolant is on. All right. We'll close the dialog, and we'll select geometry. Select the outer boundary. And you notice that there's no need to select the entire boundary. When a geometry is fully or properly connected, selecting one feature will identify the entire shape. Hold the control key, pick the island. I'm going to go into isometric view and do it. And let's see what we get. Looks like I chopped off my island there for some reason. All right, guys, what did I do wrong? Okay, much better. Here we go. We've got an island. I had my geometry at the bottom of the cut, and it went down and cut it. So there we are. There's the result I was looking for. Here's the pocket. In the new release in V9, what you can do is if you right mouse click the top of the control panel, there's a new feature called overlay geometry. If I overlay the geometry, I can actually view it before the rendering, start my rendering, and watch it cut around the geometry. So a pretty handy little addition to the software where you're able to overlay your geometry on the part and see where it's actually cutting. All right, so that worked out for us. Not too bad. So as you can see, we took out all the material, and to illustrate a little bit slower, I'm going to slow it down. Here's operation number 1. Punches a hole in the part. Then the end mill comes in right at that same location and does the pocketing. You'll pick up, go back to the same location, and do it again. goes around the island to finish it, and then we're good to go there. Next, we're gonna, now, if you notice in version 9, the do it and redo button are both active. So it's no longer necessary that you deselect the operations on the right. If you're gonna make a new one, you just click on the do it button. So you could leave these selected, make a new series of ops, hit the do it command, and not worry about overwriting these. If you hit redo it, then you have an issue. You'll overwrite the commands. I'm going to deselect simply because I'm in the habit of deselecting, and dump my processes. Got to get rid of them, make some new ones. I'm going to do the OD of the part now. This is going to be a contour cut with tool number 2. Bring down tool number 2, contour process, and feeds and speeds are good, entry exit moves are good. Stock, I'm going to leave 175 thousandths. If you all remember this tutorial part, the wall thickness of the geometry that we see on screen is going to be 150 thousandths. Instead of drawing geometry that's 150 thousandths bigger, I simply use the stock allowance to leave material and give me that 150 thousandths wall. Since this is a roughing operation, I'm leaving an extra 25 thousandths, so it's 175. Z stock is 0. Overlap will be 0 on the roughing op. We'll go with these same values here, 0.1, 0, 0.1, minus 0.5, and we're going to split this into 2 passes also. We're cutting around the outside in 2 passes, auto plunge, round corners, 0 corner break, and once again, flood coolant is on. We'll close the dialog, and then we're going to stage our finish tool. Finish tool is going to be tool number 3. I bring tool number 3 down to process tile number 2, bring down the contour tile, and as you can see, all the values are there. Everything's set for me to do it. The only change I'm going to make is make this 150 thousandths. So it takes an extra 25 thousandths off the previous cut, and I'll add an overlap of 30 thousandths. Close the dialogues. I'll go to top view, and I'm going to select my geometry right over here. Now, there's a feature in Gibbs that if you want to start right at the midpoint of the feature, you click on the feature, hold the control key, and click anywhere on screen, and that markers snap to the midpoint of the feature. Once again, here's a feature here, control click, markers snap right to the midpoint. I'm going to start on this radius in the center, like so. Okay, this is going to be a climb cut on the outside of the part, starting right here. Now, what I should have done was, let's see, I think that'll work. Let's say do it. Okay, what I'm going to do is I'm going to increase my radiuses so that they are actually outside the part. So if I wanted to start outside the part, I could do this. Change this radius to a 1 inch and change this radius to a 1 inch and redo it starting out here. And if I wanted to get really creative and start way off here, get this radius 2 inches and this one 2 inches. Now we can see that we're starting over here off the part, and we're not entering into the word. Although I would normally remove that material, and I'll show you how to do that shortly. Now, if I go to isometric, render it, you see the machining inside of the part. Then we'll come out and machine the outside. And as you can see, we've left 150 thousandths uniform wall thickness all the way around this part. Now there's extra material in these areas here. This extra material is going to be removed by first drawing some geometry on screen using the mouse tool and then doing a contour cut on that geometry. Let me illustrate how to make mouse line geometry. Turn off my cam palette so I don't inadvertently bring my markers up. Open the geometry creation palette, line and mouse line. Now, top view. When using mouse line, you can show the diameter of the tool by simply clicking on a tool. The rule is you have to be in the top view, mouse line selected, and then you can go in there and pick a tool and see the diameter of the tool. I'm going to clean this up with using tool number 2. So what I do is click on tool number 2 and I see the outline of my tool. To remove material, I give it a Z depth, in this case minus 0.5, and then I just start drawing. I want to start my cut here, go to here, here, and then maybe over here, and then I want to jump over the part. So I'll give it a rapid command, change the Z value, 0.1, and go from here to here. Then we turn off rapid, go to minus 0.5, click here, and then I can remove the balance of the material. Watching my cutter do the metal removal with the gray portion that appears on screen. All right. So as you can see, there's the rapid moves up and over the part. Now machining here, rapiding up, rapiding over, and then feeding down and machining that that portion of the part. All right. So that's the next operation. I'm going to render it once again so we can see what we're doing. And then we're going to remove that geometry using tool number 2. So turn off rendering, deselect the operations, and I'm going to leave tool number 2 where it is. And if I look at it, I'm going to leave the feeds and speeds alone, change my entry exit moves to 0 because I want to cut this on center line. My stock is going to be 0. Rapid approach is fine. Top of the cut, rapid retract, depth of cut, and we'll do it in 2 cuts, 0.25. All right. Close the dialog. Select the geometry at the start point, go on center, and we're going to follow that geometry with center line of the cutter. If I say do it, there's my tool path. You see the rapid cuts. And there is the metal removal. If you're wondering how I'm moving the image, I use a trackball or a space ball, and it's pretty handy. Here you go. The yellow represents the areas that were cut. All right, a couple more things to do, and we'll be wrapping this up shortly. If you're getting a little impatient here, turn off rendering, go back to top view. Next operation, we're going to spot, drill, and tap the 4 holes. So the first thing I'm going to do is deselect the operation, dump my process, open my work group list, and go to work group number 1, which is the original geometry. I'm going to make a multi-tool process. So once again, I bring down my spot drill, drill, and tap. I staged them all at the same time in this occasion. The holes process for tool number 1 is going to be a spot drill. Feed in, wrap it out. Now, what we're going to do is we're going to make the R plane down at the bottom of the from the top of the cut. I'm going to make this at -4. And I'm going to tell it that the stock or the cut begins at -0.5. This is 0.4, I'm sorry. So it's going to wrap it down to 400 thousandths inside the pocket. It recognizes the top of the cut at -0.5. It's going to retract to 0.1. And I want a chamfer diameter of 215. Break the edge at the top of the hole. I got to, what size is my cutter? Okay, we'll just make a hole. Yeah, 215. That's fine. Retract to Z 1 inch. And what we're going to do is leave the feeds and speeds alone, close the dialog, and set up machining parameters for the drill. The drill is a number 7 or 201 drill. This is going to be a peck with a full out. Clearance of 50 thousandths and a peck amount of the radius of the cutter as a default, 0.1005. We'll go with the same values on the rapid. Top of the cut is -0.5, and I'm going to take it to the shoulder to get through at -0.8. Feed the speeds are going to be okay there. We can always change them at the machine if we need to. And the tapping is done with the hose tile. And you notice that rigid tap is already selected for us. That is based on the tool definition. We're going to rigid tap. We're going to go down to -0.2. The stock begins at -0.5. And we're going to take it down, let's see. We'll take it down, take the point down to -0.75. Gives us 50 thousandths to the bottom of the hole. All right, close the dialog window, and then we hold the control key and pick the points in the order that we want them machined. Say do it, and take a look at the part in isometric, and we see the 4 holes, spot drilled and tapped. Start from scratch, and we can see what we've done up to this point. All right, so far so good. Now, my intention is to put a 10-degree taper on this island here. So what I'm going to do is come back, turn off rendering, turn off or deselect the operations, click off the part, and dump my processes. This next operation is going to be done with tool number 3, which is a, what's tool number 3 here? Is our 1/2-inch cutter. Bring down tool number 3 and the contour tile. Let me close the contour tile just to illustrate something. Presently, the geometry resides at the top of the part. I'm going to use this cutter to cut a taper along the side of the end mill, but I prefer to start the cut from the bottom up. So I'm going to take this geometry and I'm going to modify force depth to -0.5. Do it, and it snaps to that location. Now, what I'm going to do is open the process dialog, and I'm going to go to wall choices. This button here gives me a set of options for machining swept shapes, tapered wall with fillets, and straight with zero taper, which is the default. That's why you see the 0 here. My selection is going to be tapered with fillets. Give me the ability to create a radius at the top, side angle, and a bottom fillet. I'm going to go with a 100,000th top fillet, a 10-degree side angle, and a 0 bottom fillet. The bottom fillet will be created by the radius on the tool. I'm going to start from the bottom up in one direction, and I want a shape step of 0.01. So every 10 thousandths is going to feed upwards in increments of 10 thousandths. User defined step is a linear step over, constant step over. User defined step typically used on straight walls or slight tapers. Shape step will follow the shape closely, giving you an equal surface finish or an equal scallop height. We'll go with that value there. Close the dialogues, select the geometry, set it up for a climb cut, and we say do it. As you can see, the geometry appears, the toolpath appears based on the geometry. If I render it, we see the result at the sidewalls at a 10-degree angle there. All right. That pretty much covers this particular part. You guys all know that you can find this part in the tutorial manual. You can go in there and follow the steps. We're going to compile and post this video on our online portion of the website, and it'll be accessible if you have a username and password. All right, gentlemen, I'd like to thank you for attending, and keep an eye out. There will be more in the future. Thank you very much, and we will see you soon. Thanks a lot.